Now we can post-process the cell center values of the primary unknowns to produce useful visualizations. Instead of double-clicking on Results in the Workbench window, we will start by double-clicking Solution to reopen Fluent. Post-processing can be performed inside the Fluent interface. The Results step instead uses CFD Post, an alternative and older post-processor. Once Fluent opens, we can begin by looking at contours of pressure and velocity on the inlet and outlet faces of the structure. This helps to gain intuition for the flow while also being a useful check that our boundary conditions were applied correctly. In the Results tab on the top bar, click Contours and select New. In the new window, name this Velocity I/O. Under Contours of, ensure that it is set to Velocity, and that Velocity Magnitude is selected. In the Surfaces list, uncheck every surface except for Inlet and Outlet. Finally, click Save/Display to view, and close the window. In the view, we can see the velocity contours on the two surfaces, and use the middle mouse button to rotate the view to see each surface. Near the inlet, we can see that the velocity is nearly constant across the surface. There's a very small low velocity region along the edges of the flow domain because of the no-slip conditions from the wall. This is visible on this contour because of the interpolation within the cell, as these outer elements are part of both the inlet and the wall. If we right-click on the surface, we can see the numerical values for the contour band in this region in the console. This shows that the velocity is equal to its specified boundary condition value of 5 micrometers per second at the inlet. On the outlet, however, we can see that the boundary layers have developed more fully, creating large low velocity regions near the edges. This has caused the velocity in between to increase slightly above the inlet value. If we once again right-click to inspect the value, we can see that the velocity increased to around 7.3 to 7.4 micrometers per second. To further investigate the development of the flow along the axis of the geometry, we can visualize the velocity contours right behind the obstructions. This will help to identify how they affect the flow domain. Under the Results tab, on the left side, select Create, and click Plane. In the new window, name this XY Offset. We want to slice along the axis of the geometry to create a plane parallel to the inlet and outlet. So, change Method to XY plane. We can then choose an offset Z value. To place the plane right behind the obstruction, enter 1.6 E-7 to place it 160 nanometers from the inlet. Click Create to complete this process, and we can then close the pop-up. We can then add contours onto this plane. In the tree, expand Graphics, and expand Contours. We can then see the velocity contours we created before. Right-click to edit them, and select Edit. In the Surfaces list, click XY Offset to add it to the list, and click Save/Display to view. We can then close this window. In the view, we can again use the middle mouse button and the scroll wheel to adjust the view. We can now see 3 stages of the development of the flow. On the plane behind the obstructions, we can see the low velocity region created by the pillars. This also reveals a high velocity region in between them. Right-clicking to inspect the value, we can see that the velocity accelerates to around 8.15 to 8.2 micrometers per second in this region. This then decreases slightly as we move to the outlet. We can similarly create pressure contours on these surfaces. As before, click Contours under the Results tab, and select New. In the pop-up window, name this Pressure I/O. Change Contours of to Pressure, and ensure static pressure is selected. Again, select Inlet, Outlet, and XY Offset in the list, and click Save/Display to view. We can then close the window. In the view, we can see the pressure contours on the 3 surfaces, and use the middle mouse button to rotate the view to see each surface. We can see that the outlet has a uniform pressure distribution equal to 0. This shows that our boundary conditions have been applied correctly at this location. On the inlet, we can see that the pressure is nearly constant as well, with the small high pressure area near the edges. This is consistent with expectations for general pipe flow, with the discrepancies being small errors along the edges that will shrink with mesh refinement. On the plane behind the obstructions, we can see small, low pressure regions behind the pillars. The rest of the surface is approximately constant in pressure. This matches the expectations from pre-analysis that the pressure would decrease along the direction of flow, but be uniform along a cross-section. Next, we want to look at velocity vectors around the obstruction. To do this, we need to create a plane similar to before. To do this, select Create in the top left corner. As before, select Plane. Name this ZX Offset. We want to create a slice through the obstruction, so under Method, select ZX plane. We can then choose a Y offset value. To create a plane through the obstruction, enter 1E-7. Click Create to make the plane, and click Close. We can now work to plot vectors on this plane. In the Results tab, click Vectors, and select New. Name this Vectors. Ensure that Vectors of is set to velocity, and that color by is set to velocity and velocity magnitude. On the left side, change the scale to 0.002. This helps to reduce the size of the vectors so that they are more appropriate for the scale of our domain. Similarly, change skip to 1. This helps reduce the total number of vectors to make the visualization less cluttered. Finally, in the surfaces list, ensure that only ZX offset is selected. Click Save/Display, and we can close this window. We can then see the vectors in the view. We can use the middle mouse button to rotate the view, and click the green Y-axis in the bottom right corner to orient the view to be facing the plane. We can then use these arrows to rotate the view to better adjust for the orientation of our geometry. Zooming in, and looking near the walls, we can see the low velocity boundary layers develop. Zooming in near the cylinder, we can see the effect of the obstruction on the flow. Near the front, we can see a stagnation region as the flow is slowed, and a similar low velocity region behind it. The flow appears to move around the cylinder symmetrically from top to bottom, as expected. Away from the cylinder, we can see the high velocity regions that were present in the previous contours as the flow moves around the cylinder.